Okay, good afternoon. I would like to start. The topic that I will talk about today goes under the title of Stochastic Gradient Descent or Online Learning. I will write this down. So our framework so far, when we discussed gradient learning last time, was that we had a training error, right? And what we were trying, and this was 1 over p, sum over I, mu going from 1 to p, the error for x mu, which depends on the weights. And what we were doing was that we were minimizing this by going in steps and in each step going in the direction of the gradient. So this is a training, and this is gradient learning. This is what we did last time. But this is also called batch. This form of learning is also called batch learning. And the reason that it's called batch learning is that we have this batch of examples. And in each step, we're updating our weights based on all of them. Right? So, computationally, this is sometimes not so convenient. We might want to update after each example that we see, and it's also biologically less plausible than observing some examples and based on each example and the reward signal updating your weights. And therefore, we turn our attention to online learning. And in online learning, the idea is that at each step we're presented with examples, and the examples are simply drawn from some distribution. Drawn sequentially from a distribution P of x. And we're going to come up with some update rule which in general will have the form that the weights at step t plus 1 are the weights at step t plus some function of xt plus 1 and yt plus 1. But so this is a bit similar to technically to what we did in the Adatron algorithm, but it's different because we're not cycling through examples. We're just, each time we're drawing a new example from this distribution P of x, which might also be the general distribution from which examples will come when we generalize. And so there's no cycling through examples. And I'll write down a particular update rule in a moment. But because of this setup, it's not so meaningful to talk about a training error, because in any case, the examples that we see are, don't have one set of examples for which we're trying to minimize the error. We have examples that just keep coming in each time they're a new example. But we'll be interested in the generalization error. Okay, so the type of learning that I'm going to propose here, which is called stochastic gradient learning, is the following. We're going to set wt plus 1 equals wt minus eta, the gradient with respect to w of epsilon xt plus 1 wt. So this looks very similar to this, except that we're going in the direction of the gradient with respect to the error of the present example that we're seeing, right? So we have a certain set of weights at step wt. I give you a new example, and I want to go in the direction where my approximation of y for this particular example will be as close as possible, or the square distance will be minimized, square distance with respect to the true y. Very good. So you might encounter, when people talk about stochastic gradient descent, different versions of what is the cause of stochasticity. In our case, in the version that I'm talking about, the stochasticity is simply coming from the fact that each time we're drawing an example randomly. Yes, Daniel.
That means with the large learning parameter, we'll be only focusing on determining that, forgetting the past.
In a sense, yes. We'll talk in a moment about how the size of eta affects the behavior of this learning algorithm. So this is not really what we want. I mean, this is not what we would like to do. What is it that we really would like to minimize? I would argue that not even that. Well, our real goal is to minimize something else. So which error do we want to minimize? The generalization error. Our real goal would be to minimize the generalization error. Okay, so let's write that down. If we would do this, we would be doing deterministic gradient descent on the generalization error. And we know that that would converge to at least to a local minimum, hopefully maybe the global minimum. So if you do this, we really find a set of weights. We will find eventually a set of weights that minimize what we want, the generalization error. What is this? This is an integral, over all possible x's, p of x, epsilon of x wt.
That means we need to know the distribution of.
But we don't. Typically, we don't know it, so we're not going to do it. I'm just saying that ideally, this is what we would be wanting to do. Yes,
if you
Alex.
assume perplexity, or smoothness or something.
Right. Otherwise, yes, of course, you have to assume smoothness, and you have to, if you want to be sure that it will converge to a global minimum, then it has to be a convex problem, and sometimes it's not. But at least, this is something that will converge to some local minimum of the generalization error. This is not even that. This is, at each step we're going in some random direction. Why is this even relevant? Okay, so. And as I just mentioned, we typically, in learning problems, we don't know what is the distribution of the examples. We don't know even how to calculate this thing for any general point. We just imagine that with each example, we're given the correct answer, but we don't know the general function that we want to approximate. And so, can we relate this update rule to this update rule in some sense? Any ideas? Is there some relationship between them?
Just to make sure, the reason you didn't put a vector on the W top.
Oh, it's just because, thank you for noticing it. I'll do it. It's a vector, it's an n-dimensional vector, or I don't know, it's depending on the architecture. For now, it's for what we care, it's all the internal weight within the network that we're modifying. Okay, so is there any relationship? Is there a certain way in which this equation is similar to this equation?
If you average.
Very good. So if I look at the average, if I ask in this update rule, what is the average change in W? The average of the change in W at step t plus 1 is equal to minus eta times the average over this thing, over the inputs. Average, when I write here average, it's averaged on examples with a weight given by p of x. So this is exactly this quantity. So on average, this update rule is doing the correct thing. On average, it is. The problem is that it's only on average, and in each step we don't. In each update step, we don't do the average. We do some step, and in fact, you can convince yourself that in some sense we're doing something very bad. Suppose that our weights are converged to the minimum of this function of the generalization error. Then the average here is 0. Right? The gradient we minimize. We're already at a position which is a minimum, so the gradient at that position is 0. But if we employ this step, we will do a step. In each particular example, these are probably not the optimal weights, unless we're precisely, unless our network is precisely matching the function that we want to approximate. For each particular example, our network will not be doing exactly what we want, and so the weights will need to change in order to improve the error. So once we converge at the correct, suppose that we converge at the correct weight that minimizes the generalization error, then each step here will go in the wrong direction. So what can we expect? What is going to happen qualitatively? Let's try to draw this. We'll use this part. So imagine that this is the space of weights. We start from some step W0. We go, we're shown the first example. We go to some W1. We go from that to some W2. We go from that to some W3. So, and suppose that somewhere over here are the weights that minimize the generalization error. Okay, this is W star. So hopefully, Exactly. So at the end, it's some steady state. If we actually, approach them at some point, at some later point, we'll start to do some steps like this around them. Now, what is controlling the size of these steps? Eta. So do we want eta to be large or small? Okay. So do we want it to be large or small? For the steady state, so, okay, very good. So this is actually, we're going to get to that conclusion. But if we, suppose that we use a constant eta all the time, then do we want eta to be large or small? Well, okay, so small, because if it's small, then we will that's also true, but that's too complicated for us to think about right now, local minima versus global minima. One thing that is what has been pointed out is that we want eta to be small so that this cloud around the correct point will not be too large. We won't move around too much. Is there a reason for us to make eta large? Yeah, we just converge faster, right? So let's discuss this a bit more formally. Yes?
Kind of a confusion. You said that stochasticity comes from your free choice of the points, right, each time?
Yes.
Now, and we said that the function may not be fully convex, but have some local minima across them.
Yes.
So if you one time pick a point from one well, the other time from the other.
Wait. The wells are in the space of the W's. The wells are in the space of the weights. We consider the generalization error or any error as a function of the weight. And so you're thinking of two different spaces.
Yeah, I saw.
Right? Okay. All right, so let's think about it a bit more formally. I would like to raise some questions. One, we can ask, what are some of the questions that we can ask about what this algorithm is doing? So one is when t goes to infinity, after we've seen many examples, we're going to converge on the steady state where we hover around some point, and we can ask what is the distribution still, but our weights are not fixed. They may be now after infinite time, they will be drawn from some stationary distribution, the distribution will not change anymore over time when we observe many examples, but there will be a distribution. So we can ask what is the distribution of weights P, T of W, the probability to find particular weights after running this algorithm T steps. How does it look like when T approaches infinity? And in particular, is the average of, so let's call this, so is the average of this distribution, which I will denote by the average of W infinity, the average of W after a long time, is it close to W star, the optimal weight, or not? Sorry, where? T goes to infinity. What is PT of W? The probability, right? So our weights themselves are a stochastic variable. And we can ask, after many, many examples, what is the distribution of the weights that we'll get out of this algorithm? So that's one question. And so one question that we might want to ask is this centered at all around the optimal weights? Optimal in this sense, the weights that minimize the generalization error. We might also ask what is the width of this distribution. So, the delta, the difference of W from its mean after a long time, is this small? Okay, so this is one kind of thing that we might want to ask. Another set of questions has to do with the speed of convergence. And okay, we could also ask something like, what is the average of generalization error. This is related really to this question. What is the average of the generalization? Or, okay, we can ask question actually which is related to both. If you ask what is the generalization error after t steps, that's a stochastic variable because the weights are a stochastic variable. So we can ask how does this, for example, the mean generalization error, mean over instantiations of this learning algorithm, how does this depend on time? So what I would like to tell you is just, I will tell you a few facts which I will not prove. And all of them are related, all of them are concerned with the case where eta is small, if eta is sufficiently small. Okay? The first thing that I will just claim in words, and that I will actually show you more formally, is that when eta is sufficiently small, the stochastic gradient learning approaches gradient learning over the generalization error. Okay? And this I will show a bit later. And so what I would like to just write down here is how this quantity depends on time. And there are some assumptions here that eta is sufficiently small and some additional assumptions that I will not lay out precisely. But the characteristic behavior.
What do you mean by sufficiently small?
Okay, so
What is the quantity?
yeah, it's complicated to say. Maybe when I will show you that at least, you know, this approaches this when eta is small, it will give you some idea for how small it should be. But what I would like to claim is at least that mathematically, it's, under some conditions, it's possible to show that the behavior of this quantity, the generalization error, average generalization error, averaged over instantiations of the learning algorithm after t steps, behaves as follows. It's the generalization error of some optimal weights. Now, optimal weights, meaning when I'm saying that it's W star here, it's some local minimum of the true generalization error. If the generalization error is convex, it has just one minimum, then we're guaranteed that this will be the true weight. Otherwise, the algorithm might converge to some local minimum. But at least it's converging to some local minimum. But that, of course, this would be correct if, you know, we would truly minimize the generalization error and after infinite time. But now there are two additional terms. So, and these encapsulate the dependence on eta, when eta is sufficiently small. One is some constant times eta. And the second one is some constant times the exponent of minus lambda eta t, where a, b, and lambda are constants that depend on the problem. And so this is the behavior for large T. And what you can read out from this behavior is that eta affects two things in accordance to the intuition that we developed when we discussed this. Eta affects through the parameter A, the width of the of the steady state distribution. So even if suppose that we wait for infinite time, this term goes to 0, we're left with some additional error in addition to the generalization error, which increases when eta increases. This is because when eta increases, the size of this cloud becomes larger. Okay? So this is one effect of eta, and the other effect is that it affects the speed of convergence. This is what you see here. If eta is larger, this term goes to 0 faster. right? And that leads to the intuition that some of you had when we discussed this, that we might want to actually tune eta dynamically during the learning. We might want to start with a fairly large eta in order to allow this term to go down quickly. And then as we kind of zoom into the correct solution, start to decrease eta so that the size of this cloud will diminish. And so there's actually a theorem on this that, again, I will just mention, I will not prove. That W converges to W star, which is, let's suppose that it's convex, so it would be the argmin of EG of W. If we use a protocol in which we reduce theta to 0 as t goes to infinity, but under the following conditions. So we have to have that the sum, these are sufficient conditions, that the sum from t going to from 1 to infinity of eta t is infinite, it does not exist. So this requirement actually tells us that we're not allowed to make eta approach 0 too fast. If eta approaches 0 too fast, this sum will be finite. So this tells us we're not allowed to go too fast. The other condition is that the sum from t going from 1 to infinity of eta square is finite, is not infinite. This means that eta should not, go also too slow, should not be reduced too slowly. If both these conditions are met, we're taking eta to 0, so not too fast and not too slow, then the algorithm is guaranteed to converge to approach the minimum. And just an example, we might use a power law that eta goes like some constant a divided by t to the power nu, and nu, in order to fulfill these conditions, has to be larger than half and smaller than 1. Under these conditions, this is an example for a protocol of updating eta which will fulfill these conditions. Okay, what I would like to do next is, so this idea that gradually reducing the variability, in a sense, this is really gradually reducing the variability of the learning, the how much we change in time. This idea, I think, is inspiring also for learning in the brain, and in fact, in motor learning, it's a very well-known fact that during early phases of motor learning, there is more exploration, more variability in the motor action. And as people become better and better at learning some repeating motor action, their variability goes gradually down. If you look at athletes, for example, if you ask what is the difference between a serve of a professional tennis player and which has practiced a lot, and an amateur, then for the professional, after lots of practice, if you will film, the serve again and again, you will see that it's extremely stereotyped. Very, very little variability. But in the early stages of learning, there's much more variability. So this is a general property of stochastic learning algorithms. In those cases, in motor learning, this is not precisely, the setup that we laid out here is not exactly the relevant one with the examples and answers. The examples are generated by the learner itself, by trying various things. But the feature that stochasticity, the amount of variability goes down with learning is a desired feature in many stochastic learning algorithms. Okay. What I would like to do, just as one last thing in this topic, is to show you more formally why it is true that this becomes this when eta is small. Okay? So I want to show this formally. So maybe I'll erase this. I will leave this here for now because it's kind of the layout of the problem. So what I want to show is that formally that this becomes this when eta goes to 0. Why is that true? So again, our rules of the game are that we apply gradient, this rule, wi minus wit is equal to minus the derivative with respect to wi of the error for the example t plus 1 evaluate its w at wi, and now we want to look at the behavior for small eta. And what I'm going to do is that I'm going to compare two versions of this algorithm. In the first version, this is exactly what I'm going to do, and I'm going to call the eta that I will be using eta 0, and I'm going to perform one step of this algorithm. Okay? In the second version, I'm going to do something a little bit different. I'm going to actually perform m steps of this algorithm, but I'll make them m times smaller. So I'll choose eta to be.
You mean like in the line for that, like a generalization at all, like EG or?
No, because this is the stochastic gradient descent. I'm considering now the stochastic gradient descent. I want to show that when eta approaches 0, it becomes equivalent to minimization over generalization error. So I'm comparing one step of this algorithm to another possibility where I set eta to be smaller by a factor m, but I perform m steps. Okay? And I will make m large. All right, so what do I need to, I will focus now on this version. Okay? Now, it seems that kind of on average, this is going to be similar to this. We did one step with a larger eta, we do m steps with an eta which is smaller by a factor of m. It's not exactly the same thing, as we will see. So, what I want to write down is what is wi at step t plus m minus wit when I use this picture. So it is equal to minus eta d to dwi sum of a going from 1 to m. You have m steps, epsilon at example x t plus a and the W, the weight that I have at step t plus a minus 1. And now what I'm going to do is, first of all, I'm going to write eta as minus eta 0 over m. And I'm going to expand this thing. So our whole assumption is that eta, both eta 0 and of course eta are small. So the changes in the weights in each step are small. So I'm going to expand this around the weights at the first step. So what I'm going to write down is that this is sum d to dwi, sum a going from 1 to m, epsilon of xt plus a, wt. Okay, I replaced wt plus a minus 1 here by wt, which is of course an approximation. It's not true. The weights are changing in each one of these m steps. But I can expand, so I can do a Taylor expansion. I will start from this, and then there will be additional higher order terms. So, you know, the next term, for example, how would it look like? It would look like minus eta 0 over m, d to dwi, sum over j, d to dwj, sum over a going from 1 to m, epsilon of xt plus a, still evaluated at wt, and the difference between the weights, you know, wj t plus a minus 1 and wjt. And there are additional terms. So what I did again, I'm expanding this around wt. So the 0th order term is the one where I'm replacing it by wt. The linear terms involve all the derivatives of with respect to the elements of w times the change in these elements. But the important thing that I want you to note when you look at this is that these differences are at least of order eta. When eta approaches 0, if eta was 0, there would be no change in the weights in any step, so this would be 0. So this involves, the changes in the weights themselves can be expanded in powers of eta, and they start with power 1 of eta. And we also have or eta 0, and we have an eta 0 also here. So this is at least second order, this is a higher order in eta 0 compared to this term. This term is linear in eta 0. This is at least second order, and the additional terms will be even higher order. So as eta 0 approaches 0, eventually I can ignore this part with respect to this part. That's one thing that we need. And so I'm going to now shamelessly just do that. I'm going to ignore this part and just write down, work with what I've written here. So what we concluded so far is that when eta 0 is sufficiently small, wit plus m minus wit is approximately minus eta 0 over m, d to dwi, sum over a going from 1 to m, epsilon of x t plus a xt. Now that's much better for us to work with than what we had here, because here we're all the time, wt. Here the weights are fixed at their value at time t. So this is really just like applying m steps of what we did here, without changing the weights along the line. So my point again, in words, my point here is that when eta 0 becomes sufficiently small, the fact that the weights are changing along these m steps can be ignored. We can imagine that we're fixing wt and doing m steps in which we just use the gradient with respect to wt. This is what is written here. And now we're going to think about what this tells us. Let's ask what is the mean of this quantity. the mean of wi t plus m minus wi t is, what is it? It's minus eta 0 over m. What will we get from taking the mean of this? What is the mean of this? We did it before. So first of all, we have here, so this is a mean over, choosing the xt plus xt, right? The xt plus h. It's a mean over choosing the examples, and the weights here are fixed. So I claim that first of all that it's the same for each one of these terms. Does not depend on a, because the only difference here is the example which is drawn randomly. And what is it? It's a generalization error for Wt. So what we got here is that this is, so we have m times the generalization error of x, the generalization error of Wt. So it's minus eta 0, and there was a d to the wi, d to the wi, d to the wi of m times this, so it's d to the wi of the generalization of Wt. This shouldn't really surprise us. What we already discussed this in the case where m equals 1, that on average, when m equals 1, one step of the algorithm is like doing one step of gradient descent on the generalization error. And that's true also when we have m examples. But because I did this scaling of eta with m, this will be true, this result will be true both here and here. In both cases, it's eta 0 times the gradient with respect to wi of the generalization error. So why am I distinguishing between this and this? If I got the same result, this result is independent of m. What do you think might be different for finite m? What's the whole point in this? What I got is that it's, regardless of m, it's one step of this or one step of this, which is m smaller steps, give me on the average the same thing. What is going to be different between this and this? Yes, Daniel? Running time, but that's just worse here, right? What might be better? Okay, so what could I try to calculate here? Yes, exactly. So what I'm going to look at, fine, the mean is exactly what we might want to do, what we want to do in gradient descent of our generalization error. What about the variance? So, what is the variance? The variance of Wit plus m minus Wit. So, again, once we've done this approximation, we moved from here. We have here a sum of independent variables, right? The x's are chosen independently. The Wt's are fixed. So we have a sum over independent variables. What is the variance of a sum over independent variables? It's a sum of the variances. What is the sum? What is the variance of a constant times something? Because we have here this prefactor. We have to square the constant, right? So I have here eta 0 square over m square times the variance of d to the wi epsilon of x Wt, where the variance is over the random choice of x. And let's just call this quantity V. And there were m terms, right? There were m terms like this, so I have to multiply by m. So in the mean, we had m terms, and it was 1 over m, so we got something independent of m. Here we have, because when we calculate variance, it goes like the prefactor squared. We have eta 0 squared over m squared multiplied by m. It still decreases with m. So we have here eta 0 squared over m times v. V is really v of it's v. Let's call it vi, but it goes like eta squared 0 over m. So the point is that averaging m steps, it's actually very intuitive. Averaging m steps has, we get the same average as over one step, but within the m steps, we're averaging over m independent steps, and the variance becomes smaller. And it becomes smaller. Essentially, within these m steps, we're already sampling n different examples, so we will be closer to the gradient of the generalization error. So this is just a way to see that if we scale, what you really see here is if we make the learning rate smaller by a factor m, but we're kind of scaling time also by a factor m. We're willing to wait m times as much. Okay, we're going to observe m times examples, and we make eta smaller by a factor of m, then we're becoming closer and closer to gradient descent of the generalization error. And so if we're willing, again, to make the learning rate smaller and smaller, but wait accordingly longer, we're eventually going to implement gradient descent of the generalization error. And the intuition is that now you can take your learning epoch, divide it into smaller epochs. Each one of them contains many, many examples. So in each one of them, you're approximating very well the generalization error. You're doing gradient descent on each one of the examples, but you have many of them. So you're essentially doing gradient descent of the generalization error. So this is what I want, but I think it's nice to kind of write it down and see that we can show it formally. All right, so with this I will end the part of the course on supervised learning. It was really just a very short and somewhat superficial introduction to this topic. There are some courses in the university which cover these topics in more detail. There's the machine learning course, which I think is given by Shai Shalev-Schwartz. He also wrote a book which is nice. And that's this part. Now, next week I will not be here. I mentioned this also last time. I'm not sure yet whether on Thursday we will just have the TA session, or maybe Neta will give an extra hour, okay, instead of my hour. So we will update you through the Moodle. Okay. So see you. Oh, and then the following week, if I remember correctly, we have an extra hour on Tuesday. So we'll start at 11. Okay, so I'll see you then.
Aber es gibt immer, wo wir besser online
באמת כש-A שווה 1 פה, העברתי